Okay, let's do this question. Now, the following question has been given. Let R be a ring and U, V be two-sided ideals of R. Then statement 1, U positive V is equal to U positive V such that U is element of U and V is element of V. Number 2, U dot V is equal to UV such that U is element of U and V is element of V. Number 3, U intersecting V. So this is given, then this is the continuation. Then which of the following must always be an ideal of R? Okay, so pause the question and work it out. When we return, let's see how the solution is worked. Okay, now we have to know when is U an ideal of R. Okay, this is a very important definition or the concept check we will have to run. U is an ideal of R if and only if the following conditions hold. So condition number 1, closed under subtraction. Condition number 2 is closed under multiplication. By any R element of capital R on both sides. I'll explain to you what does this mean. Now let us check if U added with V is an ideal of R. Okay, now it is given. What is given? Given that U individually and V are two-sided ideal of R. This is given. So if this is the situation, then for say some U1 element of U and V1 element of V, we will have to test the properties. So what I'm going to do, along with U1, I will take another U2, and over here I will take a V2. So V1, V2 and U1, U2. Now since we know that U is an ideal of R, for some U1, U2 element of U, clearly U1 negative U2 will be an element of U. Also, for say some R times U1 will be element of U. So these are the two properties that we have tested for U being an ideal of R. Now coming to V, so the first property is what? So V1 negative V2, for V1 comma V2 element of V, V1 negative V2 will be an element of V. Also, second property, for some R element of R, R times V1 will be an element of V. Now this is to show that U1 positive V is an ideal of R. So now what I'm going to do is let us consider two elements, say U1 positive V1 and U2 positive V2 element of U positive V. Okay, now the first property is U1 positive V1 minus U2 positive V2 should be closed under the subtraction operation. So that's exactly what I'm doing. So this can be rewritten as, I'm going to club U1 with the U2 and I have a positive sign, and then I will club U2 with, or I would say V2 with, or V1 with V2. So this is actually U1 with U2, right? So let me reiterate it. So this is U1 minus U2 added with V1 minus V2. But we know that since U is an ideal of R, U1 negative U2 is going to be element of U, right? We just saw that. Also, since V is an ideal of R, V1 negative V2 is going to be element of V. So by this, the above, U1 negative U2 is element of U and V1 negative V2 is element of V, and there is an addition sign. So this means clearly U1 negative U2 plus V1 negative V2 is going to be an element of U, the capital U added with capital V. So hence property 1 is true. That's short. Okay, so with property 1 being true, we have to go and check for property 2. So let us check for property 2. Okay, let's go to property number 2. Now what we need to do in property 2 is that for U positive V element of U positive V and for R element of R, we need to show that R times of U positive V is, probably I will write one more step, is equal to R times of U positive R times of V, and this is in turn element of U positive V. Okay, so that's the understanding there. I hope you got that. So with this requirement, what we have to do is we will have to go into the original definition. Since U and V are ideals of R, clearly for U element of U, and R element of R times U is going to be element of U. Also, for V being an ideal of R, for V element of V and R element of R times V is going to be element of V. Now this means clearly R times U plus R times V is going to be the element of U plus V. Since 1 and 2 holds good, we conclude that, what is the conclusion? U added with V is an ideal of R. Okay, so that is the conclusion for U plus V. So we need to now go and check for U dot V. Now this is the second statement that has been given. We need to check that. Now the statement is U dot V is an ideal of R. We have to know, or we have to scrutinize this if it is really true or false. We don't know, we have to check. Okay, so condition 1, let us check condition 1. Okay, let U V be element of U dot V and say some U dash V dash element of U dot V. Then UV minus U dash V dash should be in U dot V. For this to be true, UV negative U dash V dash must be equal to some U double dash V double dash such that U double dash V double dash is element of U dot V. But this is not guaranteed. Okay, there is no guarantee. You cannot just guarantee the existence of this form U double dash V double dash. So this means U dot V dot is not necessarily an ideal. Okay, so since there is no guarantee, we cannot conclude that U dot V is an ideal. So the property 1 fails. So we can outrightly conclude the conclusion that I have just mentioned here. Let's move on. Now this is the third statement given. What is that? U intersection V is an ideal. Okay, now let me check. So I'm going to take we take two elements, say A comma B element of U intersecting B. So this means A comma B element of U and A comma B element of V. Now since U is an ideal of R, this means A minus B will be element of U. So also since V is an ideal of R, A negative B is an element of V. Okay, now since A minus B is element of U and A minus B is element of V, this means A minus B is also going to be element of U intersecting V. So that is for property 1. Now this is property 2. We need to show its validity. Now since U is an ideal of R for A element of U and R element of R, R times A is going to be element of U, right? So concurrently, since V is an ideal of R for any A element of V and R element of R, R times A is going to be element of V. Now since RA is element of U and RA is element of V, this means R times A is going to be element of U intersecting V. So this means from the above two properties validity, U intersecting V is an ideal of R. So the statements given, condition 1 and 3 alone are true. Okay, so this means only the choice D is correct. Okay, so that is the conclusion for this lovely question.